So in the previous video, we defined the Hasse symbol. In this video, we want to rephrase the statement about representation in terms of the Hasse symbol. This is for binary quadratic QP space. So the claim is that B is represented in V if and only if the Hasse symbol of V is equal to the value of the Hilbert symbol at P, minus the discriminant of V. So let's see why. Alright, so let's suppose that V has the following splitting. Then what is SPV in that case? Well, SPV in that case is just gonna be equal to the Hilbert symbol, A1, A2. We'll drop the P in the subsequent discussion because there is no chance of confusion. Alright, and what is dV? Well, dV in this case, because the gram matrix of the quadratic form is just gonna be diagonal A1, A2. The discriminant here is just A1, A2. So what we want to show is that this the Hilbert symbol of this is equal to A1, A2. Now, since the Hilbert symbol can only take a value 1 or minus 1, to show this, it suffices to show that their product is equal to 1. And that's what we'll show. We'll show that their product is going to be equal to some symbol that is equal to 1, if and only if B is represented by V. Right, so let's see, what does it mean for B to be represented by V? Well, that's if and only if the following quadratic form has a root, right, solution. But we can divide everything by B so that it corresponds to the quadratic form here in the Hilbert symbol. So this is equivalent to saying that this Hilbert symbol has value 1. Okay, so now the Hilbert symbol has value 1, and it suffices then to rewrite this as a product of this. This is the Hasse symbol, and this is just the B, minus dV. This is merely technical, so we just want to review the few properties that we use of the Hilbert symbol here. So first is that it's symmetric, clearly by its definition. But second, it's bilinear in each variable. What does that mean? So if we have AC, B, that's going to be equal to AB, multiply with CB. Because it's symmetric, so of course it's also linear in the second component. And next property is that the symbol is well defined up to a square. So if I multiply with a square in each of the components, we still get the symbol doesn't change. And finally, we have that this symbol minus B, B is 1. That means that this quadratic form always have a solution. Why is that? That's because the space, this we have proven before, the space minus B, B is hyperbolic and thus universal. So let's see how all of these properties play out here. So here we use the bilinearity in all of these steps here to pull out these elements. We just use the bilinearity. Now here I write B as minus 1 times minus B, so that I can pull this out because I want to use the fact that this is just gonna be equal to 1. And I use bilinearity to condense this so that here we have dV. This is just the Hasse symbol, right? And this is minus dV, B. And so the Hasse symbol and minus dV, B, these must have the same sign, so they must equal. Thus we see that B is representable in V if and only if the Hasse symbol is equal to the Hilbert symbol evaluated at B, minus dV.